Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hello students, so we started coordination compounds or coordination chemistry in our last lecture, our last class. So a few things we studied about coordination chemistry, just it was an introductory lecture. The first lecture was introductory lecture and this is just the outline of the chapter. Means these are the basic things which we are going to discuss in this chapter, which I have already described and it was introductory. Here the most important thing was the two like the coordination compounds and the difference between to understand the difference between coordination compounds and of double salt. Because we see when you look at the structures, usually chemical formula, you may get confused with that. So just for example, if you see this compound, this is a double salt, this is not a coordination compound. So one must understand the difference between coordination compound as the double salt. The coordination compounds, what we see the metal is ligated with certain ligands, certain ions or molecules, and there is a covalent bond between them, and that covalent bond is of the coordinate. It is a coordinate bond, means the coordinate bond is also a kind of covalent bond that we know we have already seen in the chemical bonding chapter. And the coordinate bonds, what is the difference between actually the covalent bond and the normal coordinate bond? That the shared pair of electrons are given by one entity only in the coordinate bond. However, there happens the sharing of electrons. So the coordinate bonds are also a kind of covalent bond. So we see a covalent bond between the ligand, a particular ligand, particular and the metal. And so if it is there, so that ligand is very strongly bound. It will not get ionized when the compound is dissolved in water. But however, what we see in the double salt, these ions will get ionized. For example, here this you can get the taste of chloride ions in this molecule when you dissolve this carnelize into water. So you can you can detect the presence of potassium ion, magnesium ion as well as chloride ion. In the case of more salt, or this is also called ferrous ammonium sulfate, you can detect the presence of Fe2 plus ion, ammonium ions as well as sulfate ions into aqueous solution. Similarly, the potash alum that we also call alum or the fitikiri in Hindi, you can get the taste of K plus potassium ion, aluminium ion as well as sulfate ion. So these ions will get separated. All the ions, cations and ions of a double salt will get separated, will get ionized into aqueous solution. However, in the case of complex compounds or the coordination compounds, even you see here, there are potassium ion, then iron in plus 2 oxidation state means ferrous ion as well as the cyanide ion. Here you can only detect the presence of potassium ion and you cannot detect the presence of or cannot test uh, of you cannot find the presence of ferrous ion or the cyanide ion because they are strongly bound with each other and they are not independent. This ionization will not happen. So Fe and Cn will be combined together. Similarly here, into the same thing. So this is all and other terms then we saw in the Werner's theory we started and few basic terms we understood other than what Werner proposed. And the basic terms that we understood is this is a coordination compound. So everything that is written inside a square bracket is called coordination sphere. So this COCl2 NH3 whole 4 is called coordination sphere. In this coordination sphere, there is a central ion or central metal, and this central metal is actually ligated with this chloride, two chloride ions, which is cobalt, and cobalt here is in plus 3 oxidation state. And the charge of this on this coordination sphere is also shown. This charge is balanced by one chloride ion. This chloride ion here it is called counter ion and this is called complex compound of the coordination sphere. It is positively charged here, so positively charged coordination sphere, and the coordination sphere may also be negatively charged. So in that case, for example, this we have seen K4HCCN46. This is the coordination sphere which is negatively charged, and in this case, the counter ion is the potassium ion. So the counter ion this means whatever the charge is there on the coordination sphere, the opposite charge is what is called the counter charge, and the counter charge in and carry that charge and is there that exists with this complex compound called a counter ion. Because as we know, any chemical entity or anything anywhere in the universe will not be stable if it has a charge. So something must be there to neutralize this charge. So if there is a cationic coordination is here, so there must be specific anions, and the number of anions should be in accordance, so that there is no net charge on the entire chemical compound. If it is negatively charged, so there will be accordingly the number of cations. So if this is K4, efficiency. So it means there is four negative charge on this coordination. So we need four potassium ions because each potassium ion has plus one charge. So we need four potassium ions for it. Similarly, if you have here in the case of potassium ions, if you can add calcium ions, so it will be Ca2. We require only two calcium ions because each calcium ion carry two positive charge. And so this is what happens. Now, then other terms that we look at the coordination number, and this term, what does this term mean? We'll see the definition in detail today. And this, so counter ion is the ionizable ion in this case, in the case of coordination compound. And the coordination, it is not necessary that the coordination compound or the complex compounds, the coordination sphere will always have certain charge. It may be electrically neutral as well. So in that case, there will be no counter ion. And the coordination number is means to how many atoms the central atom is directly connected to or the linked to is called coordination number. This cobalt is linked to two chloride ions and four ammonia molecules, two nitrogen atoms. So actually in all there are six atoms which are bound directly with the cobalt, so the coordination number is six. And the ligands are what? The atoms or the ions or the molecules which other than the central metal which bound to the central metal is called the in the coordination sphere is called ligand. So in this case chloride is the ligand and ammonia is the ligand. Okay. So these things that we have seen, few examples also we have seen. Let us now start study about some important terms which we will be using mostly in this entire chapter. So one should understand the coordination entity. This is one term that one should remember. The coordination sphere just now we have seen is also called coordination entity. So the coordination entity is the chemical entity that constitute a central metal which can be atom in the atomic form or the ionic form surrounded by a fixed number of ions or neutral molecules. So this example that we have seen, this is also one example. So central metal is surrounded by fixed number of molecules, in this case six molecules of ammonia. In this case, this central metal is surrounded by one chloride ion and five ammonia molecules. In this case, this central metal is surrounded by two chloride ions and four ammonia molecules. So this entity, central metal plus ligand, they together form coordination entity, or they are also called coordination sphere. So this is coordination entity. So for example, and this central metal can be in the its oxidation state can be zero or it can be positively charged and so on. So the central metal can exist in the form of ion, which is having some positive oxidation number, or it can also exist in the neutral state. Means it has no positive charge on it, so its oxidation number in that case is zero. So the for example, if you look at this example of coordination entity COCl3NH3 whole size, this entire thing in this square bracket is a coordination entity, which Werner said coordination sphere, in which the cobalt ion is surrounded by three ammonia molecules and three fluoride ions. And so the coordination entity now it can be, as I said earlier, it can be coordination entity may have certain charge, positive or negative, or it may be electrically neutral. So based on that, the coordination entity can be of three types. The cationic complex entity or the cationic coordination entity. It's complex entity, or you can also call it coordination entity. So cationic coordination entity, the example you can see here, PTNH3 whole 4, and then this entire coordination entity has 2 plus charge on it. So this is called the cationic coordination entity. This square bracket, the charge on the coordination entity should be shown after the square bracket and as a and that two as a superscript, right superscript, and right superscript. The charge is shown after the number. So this is 2 plus charge is plus plus charge. So 2, we write number first and then plus charge on it because this is a real charge. If you write the sign first and the number later, it means it is not a real charge, it is oxidation number. And the oxidation number can be a real charge or it can be hypothetical. It may not be the real charge on the atom. And this thing again, I refer we have seen this the difference in the case when we show the redox chemistry. So CONH3, the another example is CONH3 whole 6 and 3 plus charge. So this entire molecule, this entire entity, the coordination entity has the three charge on it. And what we know in both the cases, the ammonia is a neutral molecule. So whatever charge is there on this coordination entity is mostly because of the charge on the central metal. So this 2 plus charge, this was the platinum 2 plus ion, and this platinum 2 plus ion is coordinated with 4 ammonia molecules. So it will have the net charge will still be there because ammonia molecules are electrically neutral. Here in this case, this plus charge is actually because of the plus 3 charge on the cobalt. And the cobalt is having is here and plus 3 charge 3 plus charge here is also the oxidation number because of this is real in the case of cobalt. This is plus 2 is the oxidation number of platinum and plus 3 is the oxidation number of cobalt. However, the real charge is there on the cobalt. Means the cobalt 3 plus ion is coordinator or forms coordination compound with 6 ammonia molecules. So this is a hexaamine cobalt 3 plus complex. And the coordination entity can also be anionic complex entity or anionic coordination entity. It means the complex entity or the coordination entity is having a negative charge. And in reality, this kind of examples we have all seen earlier as well. So the example is here ACCN whole 6 4 minus. This is a hexacyano iron 2 complex. This is a hexacyano iron 2 complex. This is 6 CN cyanide. This is 6 cyanide ions are there, cyanide ions, and they are coordinated with iron 2 plus. So each cyanide ion is having minus 1 charge, so 6 cyanide ions are there in total. It means they will constitute minus 6 charge total, but there was plus 2 charge already on the iron. It was in ferrous state plus 2 oxidation state, and so there is a net charge of only 4 minus on this compound. So if this compound exists with the if it exists with the definitely it will exist with the counter ion. So in that case, if the counter ion is potassium, it will be K4 6 and the K4 is just to neutralize this. And the example we have already seen this in this case, K4 6 The, and you can see here the cationic coordination entity, cation and then counter ion you can see in this case. And the neutral complex entity or neutral coordination entity. The complex entity carries no charge in that case, and the examples are there. There are plenty of examples that complex entity carrying no charge. Some examples are here. Nickel tetracarbonyl complex. This tetracarbonyl is a carbonyl compound. Carbonyl compound is and this is because this is carbon monoxide molecule, and the carbon monoxide molecule is coordinated with the nickel atom. And this the carbon monoxide is coordinated with metal nickel carbon compound. And so it is just yes. So and another example is PtCl2NH3 whole twice. This is also electrically neutral. In that case, we can easily find what will be the oxidation number of nickel. It is zero because carbonyl molecule is CO. Group it is carbon monoxide molecule, and the carbon monoxide molecule has no net charge on it. It is electrically neutral. So whether 1 or 4, it will have no charge. Thus, nickel also doesn't have any charge. So nickel here is in electrically neutral state. It is not cationic. And as I said, this could be atom or ion. So nickel atom is here. In this case, iron is in the form of ion, platinum in the form of ion, cobalt is there in the form of ion as a central ion, the central metal ion. Here this is a electrically neutral state, so nickel is in zero oxidation state. and there is a PtCl2NH3 whole twice. This complex entity or the coordination entity also doesn't have any charge, but in this case the central metal has some charge and it has plus 2 charge. So there are two chloride ions that coordinated with the platinum, and the coordinate chloride ions, and there is no net charge. It means those two negative charges because of the chloride ions must be balanced by the charge on the platinum, and thus the platinum has plus 2 charge because here ammonia is electrically neutral. So this is how we get oxidation number and other things to find out. Let us now look into the central atom or the ion. So the definition of central atom or ion, we have already seen. We have already seen what is the central atom or the central ion. So here in this case, platinum is central atom, that's the central ion, cobalt central ion, iron central ion, nickel central atom, platinum central ion. So the central atom or ion, the atom or ion to which a fixed number of ions or groups are bound, and this fixed number of ions or groups to which bound to the central atom are called ligands. So the central atom or ion to which the atom or ion to which a fixed number of ions or groups are bound with the ligand are bound is called central atom or central ion. For example, if you look at this NiCl2H2O4, nickel here is the central metal atom. And when central metal ion you can tell because the oxidation state of nickel here is 6 plus 2 and nickel here is in the form of ion, so in the not metal atom, but you can call it as central metal ion. Similarly, here in this, however, in this compound, nickel is the central metal atom. To be more precise. Similarly, COCl, if you look at this compound, COCl, NH3 whole 5 2 plus the cobalt here is the central atom or ion. Central ion you can call because if you look at the oxidation number of the cobalt, it is plus 3 in this case. So there is this entire coordination entity has plus 2 charge on it and plus 2 charge plus and that plus 2 charge will be there because of the cobalt and one chloride is already there which is negatively charged. So the one chloride will also cause 1 plus charge on cobalt. So 2 plus 1 plus 3 charge is there on the cobalt. And ammonia is electric because ammonia is electrically neutral. And then this example, FeCN6 iron is the central ion. So the central atom you can also call. So central ion is iron and it is here in plus 3 oxidation state because the entire coordination entity has minus 3 charge and the 6 CN ions are there which will carry minus 6 charge. So minus 6 charge because of this and plus some charge on this iron atom. Suppose if we take x minus 6 is minus 3 and so x is plus 3 and thus iron here is in ferric state plus 3 oxidation state. The central atom or ion in this case is cobalt 3 plus, cobalt also has 3 plus charge and iron 3 plus respectively in this case. The central atoms are Lewis acids and are generally a transition or even inner transition element. So this is one important point. Usually what we call the central atoms, they are accepting these electrons, electron rich species and from electron rich species, the central atom is accepting electrons and it means it is Lewis acid, it is behaving as a Lewis acid, it means electron deficient species. So the central atoms in all the coordination compounds are Lewis acids and usually these central atoms are transition metals or inner transition metals. However, it is not necessary condition central metals like calcium and zinc, although zinc is a 3D metal, but it is not considered as a transition metal because of its properties and having and also it shows only plus 2 charge, which is more similar to the alkaline earth metal. So anyway, the alkaline earth metal like calcium can also coordinate with the EDTA, forms a very stable complex with EDTA. So the magnesium also forms coordination compounds. The coordination compound main group elements also form coordination compounds. However, coordination compounds of main group elements are not common. It is only common for transition metal elements and inner transition metal elements. Let us now see the definition of ligands and we will see also the different type of ligands. So ligands are electron donating species, and they like electron donating species means these are electron rich species, then only they can donate electrons. And electron donating species, which means they may have ions, they may be ions or molecules. If they are ions, if ligands are ions, means then it will have mostly negative charge, mostly some exceptions you can also see in some of the coordination complexes, or if this molecule is electrically neutral, then it must be having a lone pair of electrons, at least one lone pair of electrons, or it can have more than one lone pair of electrons as well. So they may be charged or electrically neutral, and that is why this ligand can be ions or the molecular form. And this is bound to the central atom in the coordination DT. So it's bound to the central atom coordination in DT. We have already seen this example. This carbonic compound. Sorry, this is the carbon monoxide is the ligand here. Chloride is the ligand. Ammonia is ligand. Cyanide is ligand. Ammonia. There are many other examples. This water and chlorides are ligand here in this example, and so on. So this ligands may be charged or neutral, like we see the chloride ion is charged, ammonia is electrically neutral, cyanide is also charged, but water is electrically neutral, so water can also behave as a ligand, ammonia can also behave as a ligand, or the cyanide or chloride, bromide, iodide, they can also behave as a ligand. Carbonyl compounds, sorry, carbon, this is a carbon monoxide, which is electrically neutral, is also a neutral ligand. The ligand may be simple ions such as chloride, or it may be a small molecule such as water, ammonia, and both are having one pair of electrons. Is having one lone pair of electrons, and water is having two lone pair of electrons. Two lone pairs means what? Four electrons. So larger molecules such as the ligand can also be larger molecule like such as this ethylene diamine. This is two amine, and this group is called one. CH2 is called methylene, another methylene, two methylene will together will call ethylene. So CH2 group is ethylene. So ethylene diamine. This is ethylene diamine. Also it's a large molecule, but it also behaves as a ligand. Or you can see even this one. So this CH2, CH2, NH2 whole size, and this entire group, three of such groups, CH2, CH2, NH2 is bound to this one nitrogen, or even macromolecules such as proteins. So proteins can also behave as ligands, and we can see these ligands are there. Some of the ions like aspartate and glutamate, amino acids which are there in protein molecules, they can also behave as a ligand. So entire since this glutamate or aspartate are part of the part of the protein, so the entire protein molecule can also behave as a ligand, which is a macromolecule, very large molecule. So ligands can be very small ions, one atom ion, the one atom ion, or a molecule, neutral a small molecule, or big molecules, or a macromolecule, that means very large molecule. So ligands can be divided into the different types of ligands. So the ligand can be chelating ligand or undidentate ligands. There are different types of ligands, and this types of ligand is actually called based on the denticity of the ligand. So ligand can be unidentate, bidentate, polydentate, ambidentate, or chelate. So unidentate means ligand bind to only one atom. So it has only one donor atom in it. Then it's called unidentate ligand. For example, ammonia. It has only one lone pair of electrons, which is unidentate, or is also called monodentate ligand. Bidentate ligand, if you see the example of this ethylene diamine, it is a bidentate ligand because it has two nitrogen atoms in it, and both the nitrogen is having a lone pair of electrons. So this ligand can bound with both the nitrogen to one metal atom, and in that case, it is having as a bidentate ligand, or sometimes it is also referred to as didentate ligand. And this is a polydentate ligand for this example. So this nitrogen is having one pair of electrons on this nitrogen, and three more nitrogen atoms are here. And these nitrogen atoms can also behave as electron donors, and so we can have four electron donors in this case. So this is called polydentate ligand. The chelating ligand, for example, chelating ligand, if both the ligands, this and this, if it is coordinated to a same metal, one metal, then this kind of phenomena is called chelate formation and chelation. And so this will behave as a chelating ligand. So didentate ligand or bidentate ligand and polydentate ligands can behave as a chelating ligand. So ligand can be chelating or ambidentate ligand. So ambidentate ligands have two donor atoms, but at a given time only one donor atom will coordinate with a given metal. So although it is ambidentate has two donor atoms, but only one atom will coordinate to the metal at a given time. And so ambidentate ligands are also a kind of unidentate ligand. Let us now see the definitions and as well as the examples of different types of ligands. And this definition or this classification of the ligand is called denticity of the ligand. So unidentate or we can also call the monodentate ligand. So what is the unidentate ligand? So it is a ligand with one donor site. So it will have only one donor site and the ligand bound to a metal ion to a single donor atom. That is what the ligand bound to metal ion to a single donor atom. The chloride ion it is anyway monoatomic ion, so it will have a single donor atom coordinates to metal, central metal. Water coordinates only through oxygen atom to a central metal, so this is also a unidentate ligand. It doesn't coordinate to the central metal through hydrogen. Mhm. Now the ammonia also has nice lone pair of electrons and ammonia also coordinates to the central metal to nitrogen. So when one atom is coordinating to the metal or forming a coordination bond with the metal. So these ligands are called monodentate ligands or unidentate ligands. Now let us see the example of bidentate or didentate ligands. Bidentate ligands, as I said, are also called sometimes didentate ligands. And this ligand has two donor sites. And the example I have already shown, ethylene diamine. This example is this nitrogen also has one lone pair of electrons. This nitrogen also has a lone pair of electrons. And both the nitrogen can be had as a donor. And so this ligand is having two donor atoms. And so it is called ethylene. It is called didentate or bidentate ligand. So it has two donor sites and it coordinates to the metal or central metal. So both the sites in a given compound, so it is called didentate ligand. Another example of didentate ligand is the oxalate ion. This is oxalate ion and oxalate ion it coordinates to the central metal is called oxalate. So this is also a bidentate ligand. Usually it behaves as a bidentate ligand and both the O minus ions coordinate to the central metal. So here we see one bond to the central metal, here another bond, and so it will behave as a bidentate or didentate ligand. Now let us look into the polydentate ligand. When more than two donor atoms are present in a single ligand, if it is two donor atoms, then it is called didentate, and if more than two donor atoms are there, then we can simply call polydentate. Or depending on how many atoms are there, then we can define it. If it is two donor atoms, tridentate, four donor atoms, tetradentate, five donor atoms, pentadentate, six hexadentate, and so on. So if you look at the example of this example, nitrogen CH2 CH2 NH2 whole 5. So three nitrogen atoms here and one nitrogen atom here. Overall four nitrogen atoms, and this nitrogen atom is having a lone pair of electrons and other atoms carbon and hydrogen do not have any lone pair, so these are not donor atoms. So we'll have four donor atoms in this ligand, and so this is called tetradentate ligand or more commonly polydentate ligand. This is a EDTA and which behaves as a hexadentate ligand. EDTA is ethylene, this is ethylene, diamine, this is diamine, and this diamine is associated with six tetraacetate. This is acetate. These are just acetate, four acetates to tetraacetate. So ethylene diamine tetraacetate. It means what? The ethylene diamine is here. If you replace all the hydrogen atoms of ethylene diamine acetate group, so we will get EDTA. So in this nitrogen is donor, so nitrogen in this EDTA will also be donor. And now as we see, this is a one carboxylate group. So this is also one carboxylate group. So four such carboxylate groups are there. So we'll have four donors here. And then other carboxylate group here, two donors are only here. One carboxylate donates only one link group, only one atom with any metal. So here the four carboxylate groups are there. So we will have four donor atoms here. Each carboxylate one donor atom, one minus ion, and two nitrogen, two donor atoms have nitrogen. So overall six donor atoms are here. So one can also call it as hexadentate ligand. And hexadentate means ADP is hexadentate ligand. Or this hexadentate is also called commonly a polydentate ligand. Let us now see the example for ambidentate ligand. Ambidentate I have already defined and already explained what is the meaning of ambidentate ligand. So such ligands is the ambidentate ligands have two different donor atoms. So such ligands have two different donor atoms, but either of two ligands, either of the two ligates in the complex, but only one of the two ligates in the complex needs to coordinate to the complex. For example, if you see this nitrito, nitrotrito, the structure of nitrotrito is like this. Nitrogen also has a lone pair of electrons and oxygen also has lone pair of electrons. So this nitrite can also be called nitrite. So ligand is goes into this one, forms complex with any metal and is a nitrite ion. And this nitrite ion can has oxygen donor as well as nitrogen donor. So this is coordinate either in the say, compound. If you see this compound is coordinated to the to nitrogen to the central metal. So this is called nitrito N. And in another example, it can also coordinate with the metal to oxygen atom. So two donor atoms have different donor atoms are there, nitrogen and oxygen, and it is complex compound. Only one of which is coordinating to the metal. So such ligands are ambidentate ligands. In this case, it is oxygen atom which is donating electrons to the metal, and in this case it is nitrogen atom which is donating electrons to the central metal. So this ligand is called nitrito N and this one is called nitrito O because oxygen is the donor atom in this case. And just to differentiate between these two different ligands means the bonding mode of nitrito nitrite ligand, nitrite ion, different bonding mode for nitrite ion. We just mention the name of the donor atom. So nitrito O means if you written nitrito O in a given compound, it means you should easily understand that it is oxygen which is donating atom of the nitrite ion which is donating electron to the central metal. And if it is the ligand name is written as nitrito N, then you will easily understand it is the nitrogen which is behaving as a donor atom to the central metal. Similarly, if you look at the thiocyanate, this is the SCN minus single minus is thiocyanate. This is thiocyanate ion. SCN minus is thiocyanate ion. And sulfur also has a lone pair of electrons. Nitrogen also has a lone pair of electrons. So both can be had as a donor. And in that case, what will happen? If yeah, either sulfur or nitrogen in the given coordination compound coordinates with the metal, then it's what is called ambidentate ligand, and one can see the example here. In this case, sulfur is donating electrons to metal, so it is called thiocyanate. So sulfur means donor is sulfur, and if the nitrogen donates electron to the central metal, one can call it as thiocyanate N. This means the nitrogen is the donor in this case. Let us now look into the chelating ligand. So the examples of chelating ligands, some examples in the definition I just explained few minutes ago. So let us now see it into, about it in detail. So when a di or polydentate ligand, di or polydentate means di means two donor atoms, then a polydentate is more than two donor atoms if there are in the ligand. So when a di or polydentate ligand uses its two or more donor atoms simultaneously, all the donor atoms are used simultaneously to bind to a single metal ion. If it binds to different metal ions, then it is not called chain. So if it binds to a single metal ion, all the donor atoms through more than one, or means two or more donor atoms, that the ligand binds to single central metal, then it is said to be a chelate ligand. Then the ligand is called the chelate ligand. And the number of such ligating groups is called density of the ligand. And this density of the ligand I have just explained. So this example, one point I forgot to mention. So this is called the all the definition we call the density of a ligand. And this is represented with the Greek letter kappa. And that is what is called kappa notation. If the ligand is monodentate, we will write kappa and 1 as a superscript. So kappa to the power 1 is called monodentate is ligand are represented as that. And didentate ligands or bidentate ligands are represented as kappa to the power 2. Hmm. And the tridentate kappa to the power 3, kappa to the power 4 for tetradentate and so on. So let us now get back to the chelating ligands again. So the number of such ligandic groups and the, whatever the ligating groups that are there in the polydentate ligands which are binding to a single metal ion, it's called NTCP, and this NTCP we have the seen the example and as well as definition. Such complexes where we see the formation of the chelate or the chelate, where the chelate ligand forms a complex are called chelate complexes. And these complexes, chelate complexes, are more stable than similar complexes containing unidentate ligands. So if the similar complexes are there with the unidentate ligand, then such complexes means the unidentate ligands are not that stabilize the chelating ligand. For example, what does this mean? If you there is a complex where ammonia is the donor atom, sorry, donor molecule is behaving as a ligand. So ammonia, which is nitrogen, is the donor atom and it also bound to the hydrogen. And another example, if you see, the ethylene diamine is the donor is behaving as a ligand. So ethylene diamine has two NH2 groups. And again, the nitrogen is the donor atom and nitrogen has only one pair of electrons. So when ethylene diamine forms a complex with any metal, so the ethylene diamine complex will be more stable than the complexes of ammonia. Similarly, if you look at the diphosphine or phosphine ligands, the PHC or anything based on the phosphorus, the PPH whole size, if you replace hydrogen with the phenyl group, will if it forms a complex, and if you form a complex with PPH2, then CH2, CH2, PPH2. So in that case, it is the bidentate ligand. If the phosphine is there in the form of bidentate ligand, or not, in that case, and if it combines or if it coordinates to the same central atom, so the chelate formation will happen, and because of the chelate formation, you see the complex stability will be more. And why the complex stability will be more? The region is mostly the entropic region, and that you don't have to go into the details. Just remember the region mostly is the entropic. Because of that, lesser entropy cause the stability goes down. Lesser entropy cause to form the second bond more precisely. So the more the number of chelate rings, more the stability of the complex. So the chelate ring things are more, the complex stability will be more. So example, if you see the example, if this complex ethylene diamine forms a complex. So if there will be one chelate formation, only one ring. However, if you see this complex formation, you will see four chelate ring formation happens in this case. Four donor atoms are there. So one CH2 NH2, CH2 NH2, another one CH2 NH2, and so on. So at least mm, three chelate rings will be formed in this case. To actually count how many chelate rings will be formed in this case, we have to make the complex. Just at least there will be at least three chelate rings that will form in this case, that one can say. And so the number of ligands, the chelate rings is more, then the complex stability will be more. So in that case, this one forms a complex with a given metal, and this one forms also a complex with the given metal. If the metal is same, then in that case this complex will be more stable. Complex with this ligand will be more stable. So this means the number of such ligands, so the such complexes, so the more the number of chelate rings, the more the stability of the complex. The stabilization of coordination compound due to chelation is known as chelate effect. And as I said, the chelate compound for chelating complexes are more stable. And so whatever the stability that we see because of the chelate formation is called this stability is called chelate effect. So because of the because of the chelate effect, the stability of the complex has gone up or the energy has gone down. And the example of the chelating ligand, very classical example is the 4,5 ring. Another other chelating ligands we have already seen. EDTA is also a chelating ligand. And so what we see the EDTA, it can form complex, it's a hexadentate ligand. So one this will bind to metal, this will bind to metal. One chelate formation, this and this, another chelate formation, this one and this one, another chelate ring formation, three, and this 4, 5, and so usually we see 6 fillet rings are formed in this case. Usually, at least five rings one can easily imagine. One between this, another between this, another between this, another this, another this. So at least five chelating rings are there when EDTA forms a chelating complex with zinc or calcium ion or so on. So this chelating complex, the coordination of EDTA with the calcium ion is one property which we use, uh, which we use in removing the hardness of water. So let us now look about this another chelating ligand, very classical example of the chelating ligand is the chelating ligand in the porphyrin ring. In this porphyrin ring, what we do is this is the pyrrole molecule. This is pyrrole molecule. Okay? And this pyrrole molecule is pyrrole molecule. Now what? Before pyrrole, such pyrrole molecules are there. They are also connected with each other, and so it forms a ring. It's called porphyrin ring. And the compounds of where we see the coordination compounds of the porphyrin ring are called porphyrins. So porphyrin, if it is written porphyrins, it means it is the chelating compound of the porphyrin ring. So porphyrin rings are complexes containing a form of porphyrin molecule. So if such forms are there and such structure, skeletal structure are there, there may be other differences, but if you see this basic skeletal, it means a porphyrin ring is there, a porphyrin is there, and if you see any complexes, and in that case, then such complexes are called porphyrins. The example of porphyrins are hemoglobin B, chlorophyll A and B, etioporphyrin ring, DPEP, they are all porphyrins. So important biomolecules like heme and chlorophyll are porphyrins. So heme, we see heme in this case, this is porphyrin, basic skeletal is there. However, we also see substituents, some substituents at different positions. And the iron, this porphyrin is ligated with the iron metal, where iron is the two oxidation state. Once oxygen molecules are bound with this iron, so iron goes into plus, goes from plus to plus 3 oxidation state. And usually in this case, what happens, iron in if the iron is in plus 2 oxidation state, its size is little larger, and it will not fit completely into this cavity with a space. So it will be slightly above this plane, above the plane of this porphyrin ring. But once it becomes plus 3 means it gets oxidized because of this, because of the coordination of the oxygen molecules. So this iron becomes its size plus the oxidation state, its size becomes smaller, it gets shrink. And once it gets shrink, it fits perfectly into this small gap, and so effects are then coordinated compound will be formed. Anyway, so those things are not here. You don't have to read about this structure of hemoglobin and how hemoglobin carry oxygen from lungs to the blood. These things you might read in your biology class, but not up to these details or the mechanistic details. Only you will have to perhaps remember the hemoglobin carry oxygen from lungs to the tissue, and that hemoglobin binds and forms coordination compounds with three part of the hemoglobin. And somewhere we see the globin protein is there that binds to this complex. And the chlorophyll A, this is the chlorophyll is R group here is CH3, it is called chlorophyll A, and if R becomes CH2, this is the chlorophyll B. The chlorophyll also C which is porphyrin, and the porphyrin then this is ligated with the magnesium ion. So in etioporphyrin we see the central metal is vanadium. In DPEP also the central metal is vanadium, only we see some structural difference at this point. At this point, is certain structural difference other than everything is the same between porphyrin and DPE. Let us now look into hapticity of ligands. So hapticity is another term about the ligand. The hapticity is the coordination of a ligand to a metal center via an uninterrupted and continuous series of atoms. So if there is uninterrupted continuous series of atoms and which bound to the central metal, and such things are called hapticity of the ligand. So if there is a ligand which has uninterrupted pair of atoms or uninterrupted series of atoms which can ligate through the metal, central metal, then such ligands, that such behaviors are called hapticity of the ligand. So hapticity is represented with this sign, which is called eta. It's a Greek letter eta. And for example, if eta 2 if you represent and if you put any power of the superscript to it, it means it represents how many atoms are there in continuum which are actually donating to the central matter. If it is theta 2 means it describes a ligand that coordinates to two contiguous atoms or two consecutive atoms, two continuous atoms. So in general, eta notation only applies when multiple atoms are coordinated and only if the only two atoms are coordinated. Then so, and similarly, eta 3 describes a ligand that coordinates to three contiguous atoms. Note here that ligands coordinating to multiple atoms that are not contiguous or not continuous, not consecutive atoms are considered identicity. Or the identicity we have already seen polydentate ligand. So the donor atoms are already there in this case, but these donor atoms are not continuous. One donor atom is here, another donor atom is here, another donor atom is here, and in between there are many atoms. Right? Also, they are not continuous atoms, so this is called denticity. And if these atoms are continuous, then it is called hapticity of the ligand. For example, ethylene forms a complex with any metal. So we see such compounds as eta 2 because both the carbon atoms are now bound to the metal. The carbon atoms of ethylene bound to the metal. Even if the propylene forms a complex with metal, in that case only the carbon atoms which carry with pi bond coordinate to the metal and both the carbon atoms are continuous, they are contiguous, and so this is also eta 2. And this is also represented as eta 2 ligand. Eta 3 ligand is this is allylic free radical. So if this is CH3, if you remove one hydrogen atom here with one electron, means if you do cumulative cleavage here, so there will be one odd electron at the carbon. Now that odd electron, this carbon can also coordinate with the metals that you can see here. And these two carbon atoms are also binding to this. Means this pi electron, pi bond is donated to the metal. And so this pi bond, although this bond is the sigma bond, bond between metal and the pi, bond of the ethylene or propylene is also the sigma bond. However, the pi bond of the ethylene is taking part into this complex formation. This is butadiene, and the butadiene we have two double bonds and the two conjugative double bonds and two conjugative double bonds. So this atom, this atom, this atom, this atom, all the four atoms will in this case, representative case is now coordinating to the metal. So this is called eta 4. So this is eta 2 means dihaptic complex. This is also dihaptic complex. This is trihaptic complex. This is tetrahaptic complex. And then pentadiene, cyclopentadiene. This is cyclopentene and it's cyclodipentene. And if the cyclodipentene, if you remove one H plus, sorry, one hydrogen radical, then it is cyclopentadienyl radical and cyclopentadienyl radical forms eta 5 complex with a metal. Usually, eta 5 complex is more stable. And the example of such complex is a lot there, and such compounds are also called metallocene. Such compounds are called metallocene. If you see any metal and cyclopentadienyl complex formation, then such compounds are called metallocene. Usually normally. So we see all the five carbon atoms of the cyclopentadienyl is coordinated to this metal, coordinating to this metal. So this is called eta 5. So eta 5, all the five carbon atoms are now bound to this metal. Let us now look into another terms like called bridging ligand and the terminal ligand. So bridging ligand and terminal ligands are also two terms which are important. So a bridging ligand is a ligand that connects two or more atoms usually, and these atoms are metal ions. So a bridging ligand is a ligand that connects two or more metal ions. I could directly write two metal ions, two or more metal ions. So such ligands are called bridging ligand. If you see this complex, you see the fluorine. Fluorine is now coordinated to this ruthenium and this ruthenium, two different metal ions. And so this fluorine is called a bridging ligand. This fluorine is also a bridging ligand. So it is also coordinated to two different metal ions. The bridging ligand may be atomic or polyatomic. So it is here in this case it is atomic. And the polyatomic is the carbon monoxide forms carbon monoxide molecule We have as a bridging ligand, so it will be the example of a polyatomic bridging ligand. So in naming a complex wherein, so when we will see the how one can write the name of the complex compound as per the IUPAC recommendation. So in naming such bridging complexes wherein the single atom bridges two metals, means the single ligand or single atom bridges two metals. The bridging ligand is preceded by a Greek letter mu, which is a mu with a superscript number denoting the number of metals bound to the bridging ligand. So this is what this chlorine is what? It is mu2. Mu2 means it is coordinated to two metals. If it is coordinated to three metals, then it will be represented as mu3. This is just remember this is mu, this is eta. And another thing we have seen density represented as kappa. So mu2 is often denoted simply as mu because anyway we are talking about the bridging ligand and bridging ligand will only be there if at least the ligand is bound to two different metals. So mu is sometimes also simply denoted as mu. And ligands that are not bridging are called terminal ligands. And so this chlorine here is the terminal ligand. So all these ligands are terminal ligands. They are not bridging ligands. So all the examples we have not taken they are terminal ligands in the complexes. So these are all terminal lines. Terminal lines, terminal lines. So the mono coordination compounds usually when you see all the ligands are mononuclear coordination compounds. Sorry, coordination compounds are mostly you see there the terminal ligand. So the example we have already seen. Let us now look into some other important terms. Oxidation number of central atoms. So the oxidation number of central atoms in a complex is defined as the charge it would carry if all the ligands are removed along with the electron pairs that are shared with the central atom. So for example, whatever the ligand that is there that is bound to the central metal, if this ligand departs from the central metal through the shared pair of electrons, then whatever the charge, the remaining charge will be there on the central metal will be considered as its oxidation number. For example, if you see this compound CuCl NH3. So this ammonia, the donor ammonia is the donor here. So nitrogen ammonia has donated lone pair to cobalt. So the donor, whatever the shared pair of electrons, although it was of the ammonia, so if it takes away, it departs away from the central metal. The central metal will not acquire any charge on it. However, because ammonia has taken away its electron, lone pair of electrons, and it is electrically neutral, which has taken away one of its electrons. However, if you see there is a covalent bond between this chloride, this chlorine, and this cobalt. So chlorine it has it has seven electrons in its valence. So if it has seven electrons in its valence share, so if it forms a one covalent bond with this cobalt, so what will happen? So in that case, when chlorine has to depart, it will take away the electrons of cobalt as well. So once it runs away, it departs away, just to assume. So what will happen? This will become chloride, and so the cobalt molecule, the cobalt atom will have plus one charge because of this COCl bond. However, there will be no charge because of the ammonia, and there is two plus charge already there on this complex. So the oxidation number of this complex will be plus two. In this case, what will happen? This is cyanide, Cn, and if the Cn minus, this is Cn minus ion, Cn minus ion it exists in the case of the form of minus ion. Now all the Cn minus ions depart away from this. So what we will see? The six minus charges coming away, and these six minus charges are balanced by this. And so what will six plus charge will be there? And six plus charge plus three charge. So plus minus three charge. So plus three charge will be there on this metal. So a Roman numeral represents the oxidation number in parentheses following the name of the coordination entity, and means the oxidation number of the metal is known in the Roman numerals in parentheses after the metal. For example, the oxidation number of copper in Cu C minus charge is plus 1. And here it is plus 1. Why it is plus 1? Just uh, and it is written as Cu and Roman numeral I. I represents 1 in the capital letter. So let us see how it has plus 1 charge. So the Cn minus these 6 Cns are there. 6 Cns are there, and all these Cns will run away with the donated electron or the electron pairs that share with the copper. So this is a Cn, and now it is running away with the negative charge of the copper as well. So what will happen? It could have copper could have plus 4 charge. And now we have removed this and removed this. However, this charge is still there on this. We have just taken away one by one, Cn minus, Cn minus, Cn minus, and Cn minus in 4 different steps. So what will happen? Once you remove the Cn minus, the copper will have plus 1 charge here and 3 minus charge here. So it means it will have 2 minus charge. Another then will become 1 minus charge, another it will become 0 charge, and then another if you remove it will become we have plus 1 charge. Now similarly you can see, so there are two different approaches to calculate the oxidation number of the central metal. Those approaches are not there in your syllabus, and so I will not discuss this. So the covalent approach as well as ionic approach, so those approaches are different, and so anyway. So one thing just only you can see is simply whether the ligand is usually negatively charged or electrically neutral. This is Cn minus ion. If it is negatively charged, so you can see correspondingly what how much charge would be there on the central metal. And considering the charge on the coordination entity as well, and thus you can find out the oxidation number of the central metal. Let us now look into the coordination sphere. And the coordination sphere is nothing but coordination entity that we have described earlier. So the central atom or ion and the ligand attached to it are enclosed in square brackets and is collectively termed as coordination sphere, and this is also called coordination entity. So here the central atom or ion and the ligands attached to the central atom to it are enclosed in a square bracket, the same thing that we have seen for the coordination entity as well, to a square bracket and central metal as well as all the ligands. And so this is called coordination here. So the ionizable groups are written outside the bracket, and the ionizable groups are what? They are counter ions. If the complex entity is having plus charge or minus charge, some charge on it, so there will be counter ions in it as well. And so they will be written outside the parenthesis. For example, we have already seen, for example, the complex K4ACCN6. This is the counter ion. So the counter ion is cation in this case, and this is written outside the square bracket, and this group is called ionizable. The coordination sphere in this case is ACC4 minus, and the counter ion is A plus. The example, another example where you can see the coordination sphere is positively charged. You can also see we have already seen earlier. Let us now look into the coordination number. The coordination number of a metal ion in a complex is defined as the number of ligands donor atoms. So number of ligands donor atoms to which the metal is directly bonded. So how many number of ligand donor atoms to how many number of ligand donor atoms a metal is bound directly, or the central atom is bound directly, is called coordination number. For example, in this complexity, the iron is bound to 6 Cn groups, and it is bound to the carbon atoms, so this is linked to only carbon atoms. So 6 atoms are linked to iron, and so this is what the coordination number in this case is 6. Similarly, coordination number of this complex NiCO4 is 4, because 4 carbonyl groups are attached to the carbon atom, to the methyl. Here in this case, the coordination number is also 4, PPCl2, 2 fluorine, and 2 ammonia molecules. The coordination number is 4. In the case of bidentate ligands, you will have to count how many, you will have to count the number of atoms which donates directly or which links directly to the central metal bidentate and polydentate ligands. So if the ligand is behaving as a bidentate ligand, so because of one ligand we see two coordination number, because two atoms are coordinated to the metal. So if there is a, suppose you see here ethylene diamine whole size. So in that case, even though ethylene diamine whole size is there, but the coordination number of iron in that case will be 6, because we have 3 ethylene diamines, and each ethylene diamine has 2 donor atoms. So overall CH3 and diamine will amines will have six donor atoms, and so the coordination number is six. And EDTA forms a complex CH complex with a metal. So what will be the coordination number? It will be six because EDTA itself is a single complex ion. It has a single large ion, not complex ion. So single large ions has six different donor atoms and six different donor atoms, and all these donor atoms will be linked in the metal like zinc and for calcium, as I said. And so the coordination number in that case of the metal will be six. Note here that the coordination number of central atom or ion is determined only by the number of sigma bonds formed between the ligand with the central atom or ion. Five bonds between the ligand and the central atom are not considered for counting the coordination number. And here in this case, one should understand five bonds, fifth bond between metal and this is the sigma bond. First bond is also always single sigma bond, even though the five electrons are taking part in the bond formation. So third bond is sigma bond, and so this is called the coordination number. This will be counted into the coordination number, and because of this, the coordination number is two because two carbon atoms are found. However, what we see also, and according to the Chat-Jensen model, which is not there in the syllabus, is metal ions also donate some electrons to the pi star of this ligand, and once it coordinates to the pi star of the ligand, metal back bonding, and that back bonding is of the pi type, and so that is not considered as another as a coordination number. Only sigma bonds are considered in counting coordination number. Similarly, if the chloride is there, it is or the water is double phase ligand, so it can donate even two of its lone pairs of electrons, and so the double phase ligand and so on. So, but in the counting coordination number, we count only one for each water molecule, even if it behaves as a diphase ligand. Let us now look into the homoleptic and about the homoleptic and heteroleptic complexes. So it's not homoleptic, it is homoleptic, and this is heteroleptic, it is not heteroleptic. So homoleptic and heteroleptic complexes. If all the ligands in the metal are of the same type, then such complexes are called homoleptic complexes. And example you can see cobalt hexaimine complex. All the ligands here are with ammonia. So the ligands, all the ligands are same. So this complex is called homoleptic complex. In this case, PPCl4, all the ligands are fluoride, and so this is also a homoleptic complex. And the heteroleptic complexes, there are two or more than two different types of ligands that belong to the central metal. So, example, this CONH3 whole 4 Cl2. This is two different types of ligands. One is chlorine, one is chloride, another is ammonia. And so this complex is a heteroleptic complex. This complex is also a heteroleptic complex. CpNH3 whole twice Cl2 is also a heteroleptic complex because we see two different types of ligands binding to the central metal, and more than if the ligands are more than two different types, can also be there. We define such complexes as heteroleptic complexes. So in this case, all the ligands can be of different group. All the ligands can be differently. They can be different, and so that is also heteroleptic. Let us now see what is coordination polyhedron. And after this, I will stop this lecture. So coordination polyhedron is the spatial arrangement of the ligand atoms which are with the spatial arrangement of the ligand atoms around the metal, which are directly attached to the central atom or ion, defines the coordination polyhedron about the central atom. So, what is the spatial arrangement of the ligand around the central metal actually defines what is the coordination polyhedron. And there are three basic coordination polyhedron that are found in coordination complex or coordination compounds. One is octahedral and another is tetrahedral and square planar. However, we also observe some trigonal bipyramidal complexes and square bipyramidal complexes, but they are not so common. The most common are three. So the most common coordination polyhedra are octahedral, square planar, and tetrahedral. And this is called octahedral is what coordination polyhedral, tetrahedral coordination polyhedron. So it actually talks about the spatial or three-dimensional arrangement of ligand around the central matter. So for example, if you see CuNH3 whole 6 is the octahedral polyhedron, NiCO4 is tetrahedral polyhedron, and CpCl42 minus is square plane. So here, if it is cobalt and all the ligand is else are NH3 ammonia, and they will make the three charge. So what we say it will be octahedral complex, and this octahedral complex is also a homoelectric complex because all the ligands here are. And if you see this example, this is also a example of homoelectric complex. This is also an example of homoelectric complex. If both are all the two are homoelectric complexes because in each case the ligand is of the same type. Here all the ligands are cobalt, here all the ligands are carbon monoxide, and here all the ligands are chloride. So this is tetrahedral. This you see the tetrahedral, the shape of the tetrahedral. This tetrahedral polyhedron, and the square planar is this. This is the planar molecule. So if you remove the axial ligand from the octahedral complex, you will see a square planar. So this is what we call is the planar and the equatorial position in the square planar complex, the axial position. To remove this axial ligand, you will get the square planar complex. And so this is square planar polyhedron. The trigonal trigonal pyramidal and trigonal pyramidal we have also seen the examples in the case of inorganic compounds, other inorganic compounds that we see, like PTCl, sorry, PCl5. PCl5 phosphorus pentachloride also has this same trigonal bipyramidal. So it has five trigonal bipyramidal, so six trigonal bipyramidal. So these are the equatorial bonds and these are axial bonds, and in that case we have seen axial bonds in the trigonal bipyramidal are always longer than the equatorial bonds, and that is because of the repulsion. And so this ligand, and if there is a lone pair on this, in this case, forms in the case of inorganic compounds that we have already seen, lone pairs also will always occupy equatorial position because the repulsion in that case will be minimized. So this is trigonal bipyramidal, this is trigonal, this is triangular structure, and in that two axial positions are there, the axial position and a square pyramidal. In the, we remove just one ligand from one of the axes, and then whatever the available structure will be the square pyramidal structure. So this is the square, and this because of the axis we see formation of octahedral. If you remove all both the axial ligands, you will get a square pyramid. If you remove one axial ligand, you will see a square pyramidal. This is a square and pyramidal in the formation of pyramid. Yeah. I'll stop it here, and in the next lecture we'll see nomenclature of coordination compounds. I will see nomenclature, and then we will also discuss about the isomerism in coordination compounds. I'll stop this lecture here. Okay, goodbye. Bye.